Hey, how's it going? I wanted to do a couple more of these problems. What is this one? I asked you guys to do this one for homework, example 3. Technically it's a classwork problem, but that's okay. We'll do it. Let's start from the top. Again, we're going to start by just stating the domain and range of the original function. We're going to sketch it. Then we're going to find the inverse of it algebraically. Then we're going to state the domain and range of that inverse. Then we're going to prove that the function that we found is actually the correct inverse by composing the original function with its inverse, and then composing in the other order, the inverse getting composed with the original function, and we should show that both of those compositions come out to be x. So a lot to do. Let's do it. So first, state the domain and range of the function. It's quadratic, right? We should know that this thing is just a parabola, and as such, the domain of our function is all reals. And the range of our function, well, we're a parabola with a leading coefficient that's positive. So we're a parabola that opens up. That means our range should be from the y value of our vertex up to infinity. And the y value of our vertex is, well, some of y'all might remember that this thing is currently in what's called vertex form. It would be a x minus h squared minus k. That's your vertex form. So we actually know that h and k are our vertex. So 3 is going to be the x-coordinate, and -9 will be the y-coordinate, which I guess means that technically this is a plus k on the end, because here we do want, we want the opposite of this sign, and we want this sign we want as is. So given that that's our vertex, that would make our range -9 to infinity, including the -9. So there's your domain and range. While we're at it, let's sketch as well. So drag this down. Let's do our sketch. I just told you that our vertex is at 3, -9. So we could certainly plot that point first. Then from there, it would be nice if you were thinking about the fact that A is 1 and there's no C value in sight. So we haven't been stretched horizontally, we haven't been stretched vertically, which means, sort of the normal rules for x squared would apply. What do I mean by that? What I mean is you'd normally be at 0, 0. Then if you go over 1, you'd go up to 1. You'd plot 1, 1. If you go over to 2, you'd be up 4. And so we could sort of kind of take that same pattern and plot it. So over 1, up 1 is a safe bet. Over 2, up 4 is a safe bet. We also know that parabolas have symmetry. So if we could just imagine an axis of symmetry here, we could take this point, bounce it over. Take this point, bounce it over. And there's 5 points on a parabola, and that's more than you ever need. So there you go. There's a good looking parabola. Is it perfect? Probably not. Am I hitting the x-axis in the right place? Probably not. And that's okay. I could plot more points if I really cared, but I don't think I do. Plugging in 0 would have been a good idea. We would get 9 minus 9, which is 0. So, the origin, sure. And that would mean that what? 1, 2, 3, 1, 2, 3. So actually, I must be a really good drawer. 0, 6 are the 2 correct x-intercepts. So there, now you've got, well, how many is that? 7 points? Whatever. There's your sketch. It's not going to work. I'm going to throw this in the garbage. So we did it. We've got the domain and range, and we've got the sketch. I guess I want to say some stuff now before I even move on. The big thing that I haven't taught you guys yet is about a one-to-one function. No, I did say it. I know I taught somebody. We know that a function is a function if it passes the vertical line test. We should also know that a function is referred to as being one-to-one if it also passes a horizontal line test, and this function does not. This function fails that horizontal line test, so this is not a one-to-one function. What that means for us, as we're talking about inverse functions, is that the inverse of this function will not be even a function at all. Because if you can imagine flipping this over the line y equals x like we do, you're going to end up with one of them sideways opening parabolas. And so suddenly all the horizontal lines that caused us to fail the horizontal line test, they become vertical lines that cause us to fail the vertical line test. And so suddenly we know that f inverse is not a function. Exclamation point. So, if I were ever to ask you a question about finding the inverse of a function that wasn't one-to-one, then we oftentimes will restrict the domain. We just kind of artificially restrict it. We say, hey, if you let this function's domain be all reals, then it will not be one-to-one, and then its inverse will not be a function. So what we might do instead is restrict the domain. And you can sort of see, if you just start from the vertex and take everything to the right, then you would have a function that suddenly is one-to-one. Now you're deleting half of the function, which is pretty drastic. But still, that's what we do sometimes. We talk about, hey, just restrict the domain. Now, you don't want to lose any range values if you can help it. So you'd want to still pick, 3 to infinity. So that's what I'm going to do. So I could restrict the domain to make it one-to-one so that its inverse is a function, right? Now this question isn't asking you to do that though. So I'm not going to really do it. But you can imagine a world where maybe I would ask you to restrict the domain of this function first so that its inverse is a function. I hope you guys understood what I just said. It's certainly really, really important. I'm not going to do it now because, like I said, the question didn't ask you to. But again, we'll certainly do it at a future date. All right, but for now, let's find our inverse. Bonk. Bonk. So find the inverse of the function algebraically. Finding the inverse algebraically is just when you, f of x just means y, right? So we're going to interchange those variables. We're going to let the y variable become x, the x variable become y. And then you just solve for x. So we would add 9. Then we would take the square root. Then we would add 3. Yeah, that looks fine. So fine, we did it. We found it algebraically. Now it says state the domain and range of the function f inverse. Now, if you recall, what was the domain of the original function? Well, the original function was a quadratic, so it was all reals. What was the range of the original function? It was a parabola that had its vertex down at -9, and from there it opened up, so the range was -9 to infinity. Well, looking here, we're supposed to understand already that the domain of the inverse function should just be the range of the original function, which is -9 to infinity. And I feel good about that. That's correct, right? -9 to infinity, that jives with our radical function. But the range of our inverse, the range should be the domain. It should be all reals. And it just isn't, right? It's actually going to be 3 to infinity. If we were to sketch this thing, then we're left 9 up 3. And all we're getting is a little radical function, which goes from 3 to infinity. We're missing a whole half of our function. And so this is certainly very tricky, but our inverse, we remember, I told you a second ago, that since the original function f was not a one-to-one function, we knew that the inverse would be not a function at all. And so there's no like algebraic rule for this. You just have to understand that when you take the square root of both sides, we were supposed to generate that plus or minus. Remember that plus or minus from before? By generating that plus or minus, we now get the top half of a radical function, but we get the bottom half too, which technically makes us not a function, but at least now our range is all real numbers like it ought to be. And at least now our graph is truly a full parabola that has been reflected over the line y equals x. Without the plus or minus, we didn't really have the correct inverse. We had an inverse that was a function, but we were missing our bottom half. So forgetting that plus or minus here would be really, really bad. You have to understand that it absolutely must be there. Otherwise, none of the properties of our inverse functions hold true. First of all, we would be a function, and we shouldn't be a function. Second of all, our domain and our range would not, they would not flip-flop like they're supposed to. We wouldn't have the correct range. And I feel like there was a third thing too, but I forget. Anyway, hopefully that made some kind of sense to you. Oh, and I guess I jumped the gun because I said we were going to state the domain and range. Well, we already talked about that, so we've covered that now too. So nothing left to do now but prove that the function that we found is the actual inverse of the function we started with. So let's do that. So what was our inverse function? This. So we know we have to do this composition both ways. So I'll just go ahead and put a dividing line down the middle. We'll do one over here, one over here. Why not do f composed with f inverse? We'll do that first. That means the original function f is our outer function. So we'll have x minus 3 all squared minus 9, where we're plugging in plus or minus root x plus 9 plus 3. Yeah, that looks fine. So this should be easy peasy. Certainly right away the 3's can cancel, and then we land on the plus or minus root x plus 9. And you can see the plus or minus thing is going to clean up nicely for us because we're squaring it. So if it was excuse me, if it was positive and we square it, it comes back positive, the radical cancels. Even if it was negative, we square it, and the negative cancels and the radical cancels. No matter which sign we're sort of considering here, the plus or the minus, we're going to get just the x plus 9. And then we've got the minus 9 conveniently, so those cancel. And we get plain old x, exactly like we were hoping for. Now we do it in the other order. So this time the outer function is this radical function, so we'll get plus or minus square root x, all x. I'll open the parentheses, I guess. X plus 9 with a plus 3 on the outside. Inside of the parentheses goes the entire original function, x minus 3 all squared minus 9. So there's that. Again, we said these parentheses here were really just placeholders. You can take them away. Then the 9's would be allowed to cancel. Then you get plus or minus the square root of x minus 3 all squared with the plus 3 on the outside. Things get a little weird here. We said here that if you were to take the square root of something squared, then technically it should be x minus 3 with absolute value bars, right? Right. But then you've also got plus or minus. So what's that mean? What does that mean? I'm going to say that what that means is, yeah, if we had the absolute value bars, and then we went plus or minus, then technically we would get a second copy of this, and we'd have a pair of intersecting lines. Now this is messing with my brain more than just a little bit. So what am I supposed to do? This is supposed to clean up nicely. want to just say I can let those cancel, but now I'm not super sure. Maybe I should have thought this totally through before going on camera, but too late for that. Well, I'm sure I'm making a mountain out of a molehill. I think more what's happening here is the plus or minus maybe isn't quite a true plus or minus. I think what we're saying is for the positive inputs, for the ones that would have been positive, that come out positive, we're going to keep them positive. But for the ones that would have come out negative, we're going to want to use the negative. I think we just want to keep the half that would have been positive and keep the half, this branch here, that's the branch that gets reflected by the negative. And really we should be just on the normal. This crap wouldn't be here. That's me overthinking things. But I do want to just say, because of the plus or minus, we can treat this as being, instead of the absolute value of x minus 3, it's just normal x minus 3. And then, mercifully, we can have these cancel. This obviously is going to need a better explanation. I will try to look into exactly why we're not sweating it quite as much, or it would be lovely if one of you kids could come in and just tell me, because you cared enough to think about it and figure it out. But this is supposed to be what happens. We are supposed to land on x. We are supposed to land on x. We do have the right inverses. So everything should be hunky-dory. And that's it. That's the end of example 3. And at 17 minutes, I guess I'll stop there. I was going to do example 4, and I still will, but I'm going to stop the video here, and you guys can tune back in for example 4 if you want to. See you later.